Welcome back from training the keyword spotting model. I'm hoping you had a little bit of fun training the neural network, changing a couple of parameters, and seeing how the tiny curve model actually performs on the data set that we have. At this point, you've gone through many different stages already of this machine learning workflow. You've gone from understanding how to collect the data we're using, that's the speech command data set, and pre-processing that data to spectrograms and applying MEL filter banks. Then we made the model small by inherently picking a neural network architecture that is confined enough that it would fit on our microcontroller device. And then you've gone through the exercise of actually training the model. And now we are at the stage where we want to understand how to assess the keyword spotting model. How good is it? Obviously, it's a neural network, so you'll immediately think of accuracy. Well, of course, I'm going to look at my accuracy of the model and see how well it performed. But I want you to know that in the TinyML context, efficiency is also extremely important. Latency, power consumption, storage, and memory are all extremely critical aspects here. This is exactly why we picked the TinyCon model. But in addition to both accuracy and efficiency, I also want to touch upon aspects of looking at metrics that extend beyond just model performance or resource constraints. When you build an application, there is more than just raw accuracy. We'll touch on this soon. But I'm going to try and get you to understand a different way of looking at machine learning systems behavior. That's the critical message I want to get across in this particular lesson. Let's talk about accuracy first. First and foremost, when you talk about accuracy for something like keyword spotting, what's the task here? When I say, Alexa, I want the machine to wake up, is it waking up only when I say it, or does it accidentally also wake up at other times? Why would it accidentally wake up? Remember, it's got a microphone, it's constantly listening. And remember, sounds can be quite similar. So sometimes when someone says something that might happen to sound like it's a yes, or a hiss, and immediately causes your machine to think perhaps you're saying yes, and which might be a keyword for it. So that's this is the notion of false positive, right? So you want the machine to not have too many false positives. In other words, if you did not say the keyword, then if the device ends up triggering, you've got a false positive. So if you did not say the keyword, the machine is not supposed to wake up. It's fairly simple, right? But you also have another situation here. For example, you might have a false negative. That is, you said, okay, Google, or you said, Alexa, and the machine doesn't respond back to you. That's pretty bad. Often that'll lead to a lot of user frustration and dissatisfaction. And you don't want that because the quality of experience here is king. You've got both false positives where the machine might wake up, and you've got false negatives where the machine might not wake up. So how do you sort this balance right over here? So this is a fundamental aspect that we need to understand in terms of really knowing how keyword spotting needs to be deployed. This leads to a fundamental notion of what's called an operating curve, or our ROC curve here. Specifically, it's called a receiver operating curve, which is to say that I'm showing you on the right-hand side. That's a graphical representation to understand the performance of a binary classifier. This is how a yes or a no system is actually going to behave. So for instance, on the x-axis, I'm showing you the false accepts per hour. How many times are you falsely waking up the machine? Or how many times is the machine thinking, oh, I think they said Alexa. And you don't want to wake up because that means that you have, pretty crappy device that's always waking up and thinking you said something. And maybe when it wakes up, if it doesn't get, the follow-on words to say, for example, dim the lights, then might say, oh, I'm sorry, I did not catch that. Wouldn't that be annoying if your machine kept waking up and said, I'm sorry, I did not catch that, and kept repeating that throughout the day when you're not even communicating to the machine? So that's the false accept problem. And you want to stay very much to the left-hand side of the x-axis. You want to decrease the number of false accepts that you have on the x-axis. But at the same time, you have this problem of false rejects. So false rejects are basically those false negatives that you have. Now, false negatives are that you actually said Alexa, and the machine is not waking up. And that proves to be problematic when you actually want the machine to respond to you. Now, this might be there's a very tight coupling between false accepts and false rejects. And that's why they're plotted together on this ROC curve. What happens is that as you decrease the false accepts, you're making the system more resilient to false accept possibilities. But in doing that, you increase the chances that your machine is not actually going to wake up when you need it to wake up. And that's why as you move towards the left-hand side, the curve starts picking up. And you actually want to be able to pick a critical junction where you can sit at and where you have the right balance between false accepts and false rejects. And that's called the operating point. Every keyword spotting architecture out there effectively relies on this operating point. Someone has to tune this operating point, and you have to control that operating point very carefully, because depending on different environments, the operating point might have to shift. How do you do that? We'll get into that in a bit. But this is a critical message, is that you are walking this line between false accepts and false rejects, and you have to walk that line carefully. So given that you end up deploying these devices in many different locations, you cannot have a single fixed operating point. So it makes it virtually impossible to be able to detect precisely when you want the machine to wake up. Why? Because there's so many different environments, and billions of these devices are floating around in not just your home or your environment, but in everyone's home across the world. So how can you possibly pre-configure them for everyone's home? This is why, for instance, when you look at your Google Assistant on your device, it actually has this capability to dynamically adjust the operating point, which is called a threshold. The operating point threshold can be moved around. So you can increase the sensitivity or you can decrease the sensitivity. It depends on how your device is being used. For example, if you have your phone and you might have it in your pocket, but you still want it to wake up, then that means that you might want it to be more sensitive because the mic is kind of covered inside of your pocket. Or for instance, you might put your device somewhere near the TV in the living room where it's noisy next to the speaker. So perhaps you don't want it to be overly sensitive. Maybe you want it to actually be less sensitive, and so you can adjust this, right? That is this freedom that you have over here. And of course, there's this aspect of just how you speak the words that are coming out of your mouth, right? Whether it's the accent is something that the network has been trained for, or maybe it's just you just relaxed a little bit and you adjusted the threshold a little bit and allowed it to take a few more signals coming through. Then perhaps it would actually work better. There are many other examples, but I'm trying to get across a critical point that it's very hard to fix a particular operating point when you're shipping a keyword spotting model to customers across the world living in different contexts. So this is why typically devices will ask you to fine tune it once you start it up. It'll ask you, would you like to customize your device? And you say, okay, Google 5 times, or hey, Siri 5 times. And it allows you to customize a little bit. And part of this kind of is adjusting how this system is going, how sensitive it's going to be. And you can also manually adjust this, right? So that's the critical message. These systems have to empower the users to be able to control how the device should behave. And you will pick the operating point that's most convenient for you, and you can dynamically adjust it as needed. Now, let's talk a little bit about the efficiency side of things. Obviously, you know that latency is extremely critical because machine learning should respond quickly. Otherwise, it defeats the whole purpose. You might think that, sure, the model works really well, but I don't care if it takes 3 seconds to wake up before it can do something. And it has to be almost instantaneous. And so that's extremely important for end user satisfaction. So the responsiveness is key. And also it has to run efficiently because you don't want it to use up too much of the battery. So the latency aspect, again, this is why you want to keep the model small. And so with all these factors you're going to consider, there's of course the other aspect of memory efficiency, altogether. When we did quantization, we brought our tiny model down from 70 kilobytes in float to just 17 kilobytes in int8 format. Now, when we are talking about models, we are focusing on the model size alone. Now, take a step back and think about what's really happening in the TinyML application that's running on your microcontroller. Let me give you an example here by showing you the memory usage. This is just for example numbers over here. First, there's a bit of application code. And this is not just a neural network that's running. There is the application code that's actually getting the data from the sensor, doing the pre-processing, messaging things, saving something to some place. And all of this code takes up memory. Then you have the actual inference engine, right? In our case right now, you're using TF Lite, but as we go into part 3 and deploy it on the microcontroller, we'll introduce you to TF Lite Micro, which has got its own APIs and its own extension of TF Lite. That engine, which is a set of libraries, takes up memory because the model uses it to execute. Then, of course, you have the model that you work so hard to design and then to optimize, and that's going to take some space. But then on top of that, you have the same amount of memory that is actually needed for hosting all these dynamic variables and so forth. And then last but not least is the audio buffer. And remember, when you are capturing those signals that are coming in, you have to store the data someplace, right? Few seconds of audio signals have to be stored, and that takes up space. So you have to store that data and then process that data. And this is just an illustrative example over here. So I'm not saying that the audio buffer is the maximum size or the biggest memory consumer, but I really want to focus on the fundamental point is that while your model is a small portion of this big equation, there are many of the components that we have to keep in mind. And it's extremely important, and I'm always surprised that machine learning engineers do not realize this fundamental aspect. As you go into TinyML, it becomes even more important. And that's what separates TinyML engineers who are cognizant about these various resource constraints as compared to people who just focus on just designing the machine learning model. So keep that in mind. Think about the overall quality of experience that you have when you have a TinyML keyword spotting application. What affects that? We touched on this right at the beginning when we talked about the speech command data set. The data set that you train can't have biases, right? They always will have some kind of biases, so you have to address that. And it might only certainly work for certain type of accents if the people who contributed to that particular data set were from a particular region. Maybe they are only from America, or maybe they're only from China. If you have those sort of clusters and your data set only comes from them, well, all of your data, no matter how much pre-processing you do, is going to result in a network that only recognizes those kinds of sounds. And so we have to be very cognizant about what goes into the keyword data set. So how diverse are the users is something that we actually have to test, against. Not just assume that the data is going to be distributed because perhaps I said, oh, I got the data from everywhere. We'll go much deeper into this aspect of data set engineering, and we'll look into that carefully because it's really fundamental. Then, of course, to be tested in different backgrounds, in different environments is really important because there's no one environment that is going to have this exact same effect. I mean, each environment is going to affect how the sound actually appears at the microphone. The sound that you're hearing now is bouncing off different walls and is having a certain type of effect. And so what you're hearing might be able to compensate for that because your brain, well, it's a remarkable neural network with lots and lots of neurons. But that's not the case in TinyML. So we've got to make sure that we're actually creating data sets, that's actually going to work for this different situations. And we're going to actually where we're going to deploy the keyword spotting model. And we also do have noise, right? As I mentioned earlier, when we're talking about the speech command data set, I said that we manually inject noise in there because you actually have to simulate the noisy behavior. And that's going to be critical in order to build a resilient neural network that's capable of doing keyword spotting. All right, so we talked a lot about this sort of pipeline. Hopefully you get a taste for the fact that there are many different ways of looking at what or how our keyword spotting model is doing, right? It's beyond accuracy, it's beyond efficiency. It's about the overall keyword spotting experience that the end users have. And that's the sort of challenge that organizations like Google or Amazon or anyone else who's building these applications need to get deployed in billions of different devices that they're dealing with. Now, are there ways that we can actually improve our keyword spotting model? The answer is absolutely yes. We can do this by looking at just more than one keyword or just the keyword alone. In fact, you can look at the actual overall experience that you expect to have which is I might be having a streaming audio, for instance, and just something that I'm, is constantly being talked to. And then you've got to be able to pick out the keywords amongst the conversation. I'll touch on this streaming audio basis next. And it's very interesting real world application of keyword spotting, and will take you from just building a simple network to now actually building a network that's actually useful in day-to-day life.